good afternoon. This is CIVE632, Computational Hydraulics and Hydrology. Today is Monday, October 4th, 2021. And the topic today has to do with more on diffusion waves. We're going to be covering 3 papers that I have written over the past 20, 30 years. Okay, so as I said earlier, 3 papers. And this class, I should remind you that deals with computational hydraulics and hydrology, but the foundation of the theory is at the beginning, at the first half class. So we talked about kinematic waves, diffusion waves, and we're going to get into dynamic waves eventually also. This paper is called Generalized Diffusion Wave Equation with Inertial Effects. What is this subject? This is kind of more of the same. You'll see many of our equations repeated here, which should be easy because that means that there's not a whole lot of new material that I cover. It's all more of the same in different views, different aspects. Okay, so I've been looking at the diffusion wave since I got a hold of the Hayami paper back in the late 70s. And then with the work of Duke and all the other gentlemen that I already, people that I already talked about, you have been pretty much exposed to the concept of diffusion wave. The diffusion wave is a way of solving kinematic waves with more accuracy. And the Muskingum-Conch method is an example. So the kinematic waves are fine, but they're not the only, and perhaps, and sometimes not okay because of the issue of the numerical diffusion. So let's take a look at what we're saying in here. Generalized diffusion wave equation. So we're coming up with a diffusion wave equation which is general. In what sense? We'll see. Includes inertial effects. Yes, because Hayami's formulation does not include inertial effects. Okay? Specializations of this equation need to lead to 4 types of diffusion wave models. In other words, the diffusion wave considers the pressure gradient and the generalized diffusion includes inertia. That means it includes the 2 components of inertia. So we're talking here 3 terms: pressure gradient, convective inertia, and local inertia. The question first that we should answer is, why 2 inertias? There is only one law of inertia from Newton. And the reason why we have 2 inertias is very simple. We are looking at the problem from a Lagrangian standpoint, meaning the grid is fixed. It's fixed in space and time. And we're moving the flow across the grid, right? The grid is the reference grid. So in that case, we call that type of approach Lagrangian. I'm sorry, Eulerian. We call it Eulerian, fixed grid. And the Lagrangian grid moves with the flow. And we're not talking at all in this class about Lagrangian approaches to computation. Why? Because Professor Ponce doesn't do that. People specialize. I specialize in Eulerian frame, okay? And so that's basically it. So from that standpoint, when we deal with an Eulerian frame, another another inertia term pops up, which is a convective inertia. In other words, in the Lagrangian frame, there's no convective inertia. There's just one inertia. But in the Eulerian frame, there's 2: local inertia and convective inertia. Local inertia is the one that changes with time, and convective inertia is the one that changes with space. So we have 2 terms, local inertia and convective inertia. So what we say in here is 4 types of diffusion wave models, depending on whether the inertia terms are excluded or included. So full inertia with the 2 terms included. Local inertia when only local inertia included. Convective inertia, only only convective inertia included. And non-inertial, none of them, either of them, both of them are excluded. Why should we talk about inclusion or exclusion? Well, that depends on ease of computation. Don't forget that, the profession's been doing this for 40, 50 years, since Duke and all these other gentlemen, all these other people. So we need to consider that simplifications are generally okay, as long as they are not too bad, okay? Now, I worked enough on like in two-dimensional models to realize that sometimes people neglect one of the inertias, not just local inertia, but not this convective inertia either. Convective inertia or local inertia could be neglected one at a time. So our objective here was to figure out what were the values of the diffusivities for the four cases. And then we could compare and see, figure out what's good and what's not that good. So basically here then we're dealing with surface flows, and we like to talk about simplifications. The diffusion wave model is well established in the literature, and we mentioned the names that you have already seen. This generalized diffusion model differs from Hayami's in that the former includes inertia, while the latter does not, meaning Hayami did not include inertia. While what we're talking here in terms of what Duke had done and other people, we do include inertia. Now, the theoretical development, I am going to go over it, but not spending a whole lot of time because this is repetition of what we already seen. Besides, you can't graph the equations immediately. If you want to learn this, you're going to have to sit down with a piece of paper or a pencil and paper to work these equations on your own. That's the only way to learn. But it's good exposure, and you don't have to, like I said, you don't have to know all the details because the details have already been worked out. If you want to become a real good person in this area, of course, then redo everything. But you don't have to, because many of you are going to go into practice, and in practice is the practical. What really matters is running the GECRAS, running the HMS, and running them correctly, right? But in order to do this, the running of these models, you have to know the theory. If you don't know the theory, if somebody comes to you and says kinematic wave, diffusion wave, and you say, oh, yeah, right, I heard about that. And by the way, this happens and has happened. The Army Corps was for 20 years talking about the kinematic wave as it had diffusion. They weren't calculating it, but they said, oh, well, the kinematic wave and the diffusion of the kinematic wave. So that's very confusing for anybody that's reading that book, because are they including it? Are they calculating it or not? So they were confused, like everybody else, until Conch came up. The problem with Conch was that he wasn't taken up. He wrote his paper in 1969, and it was not until 75 that the British picked it up. And then it was not until 78 that Professor Ponce picked it up. So it took us a while to get there, but we got there, and we realized the benefits of it. And I do reiterate, because it needs to be reiterated. The benefits of the Muskingum Conch, above all the other similar methods that are around, is that it is the only one that is grid independent. Basically correct. Grid independence means when this method is grid independent, it means that it is correct to the best of our knowledge. So we have in here the number one equation is the equation of continuity, expressed in this so-called Einstein notation. I don't know why they call this. It must have been Einstein that liked it. This is derivatives. H sub x, it's the same as partial h with respect to x. So these are the Einstein notation. And then equation number two, again, is the equation of motion, also in the Einstein notation. This is called the equation of motion because, according to Liggett, it already has a continuity in there. This is interesting to realize. And if you wanted to look at the details, you had to go either to chapter 10 of my book or go directly to the work by Liggett, which I have posted for you already. So this is the equation of motion. These two equations, now we come in here with our Professor Ponce's trick. Now, I know I did not invent this trick, but I used it extensively throughout my work. Okay, the role of the inertial terms in describing the run of diffusion can be analyzed by a procedure similar to that used by Ponce and Simons. So we recast equation 2 as A and B. Equation 2 now has an A in the front of the time derivative or the local acceleration and a B in the front of the convective acceleration. So we run the math and we can get at the end, we can say A equal to 0 or B equal to 0 or both of them equal to 0 and we'll take them out. So 1 puts these terms in and 0 puts them out. That's what we used in many of the work that much of the work that we have done in this area of wave propagation. Okay, now hyperbolic system. When we get these two equations, independent equations, but we can combine them under linear assumption. We can combine them. This is what Ferrick did. This is what Hayami did. A lot of people have done that. Why is that? Because we realize, this is very important to realize. Why? Because some people don't know, they say, oh, well, I mean, it's a linear system, so you're not solving the real problem. And the answer is not correct, because the system is not nonlinear, it's quasi-linear. I already told you, quasi means almost. So the system being quasi-linear, it can be readily solved with approaches such as Hayami or Dukes. The entire book by Duke is linear theory. Okay, so there's nothing wrong about the linear theory. It's good. So when we combine these equations, these two equations, we end up with an equation number 4 that looks like that. How do we combine this? Well, it says in there, you can try it on your own. Those of you that are interested in learning this stuff, and try it on your own. Don't take my word for it. Diffusion wave equation with inertia is derived by differentiating equation 1 with respect to x, equation 1 with respect to t, and equation 3 with respect to x, and then combining them. Combining the results into a second order, we end up with this equation. But this equation has mixed derivatives. What does that mean? If you look at second order derivatives, xx, xt, and tt, that's called mixed derivatives. It's a full-blown equation. And what is the v? Actually, I didn't change this. In the Helvetica font, the nu shows up as velocity. So it's kind of confusing. But I do not want to change to Roman. I could have changed only the nu, the v to Roman, it would show up as nu. But I didn't do it. So I had to take my word for it at this time. The v over there is not velocity. It is nu. It's supposed to be nu in Helvetica font. Okay, so we have the 5 here, which you already know. This is Hayami's equation. We have 6, equation 6, which is the fruit number. No? Now, it can be readily shown that equation 4, the one that we derived here, is parabolic for the special case of A equal B equals 0, and hyperbolic otherwise. What is this parabolic hyperbolic? You would recall from your high school algebra that the second order equation, the second order algebraic equation results into parabolic or hyperbolic or elliptic solutions. Remember, hyperbolic with 2 answers, parabolic with 1 answer equals 0, and elliptic when it has no answer. It goes into the imaginary domain. So the same way it happens with strictly algebraic equations, it also happens with partial differential equations. They have the discriminant b squared minus 4ac and so forth, you know, all this stuff from algebra. Okay, of course, the b squared minus 4ac are not the a's and b's that we're talking about here. I don't mean to confuse you. In here, the a's and b's are my trackers, my tracking numbers or tracking digits. But it's parabolic when a and b do not exist, and hyperbolic otherwise. What's the difference? A parabolic solution has only 1 answer. Hyperbolic has 2. Ponce and Simons have shown that shallow water flows are weakly hyperbolic. Secondary wave associated with the C- characteristic. Weakly hyperbolic is that, yes, they have 2 answers, but one of them is so small that it doesn't really quite get into the picture. It says associated with the C- characteristic featuring a high degree of dissipation through a wide range of dimensionless wave numbers. We go back to our S-curve. That's why our S-curve is so important. Such a mechanical system is readily amenable to conversion to a parabolic analog, which ostensibly can propagate in only one characteristic direction. Don't get too confused about the characteristic directions. The characteristic direction is the grid that follows the flow, more or less like Lagrange, by the way. But we're not dealing with it. So this is kind of just a way of saying it correctly. parabolic analog to the hyperbolic system. So now we do some more math in here. To this end, equation 4, which is over here, is differentiated with respect to space and likewise with respect to time, and with the neglect of the third order terms justified by the usual license of differential calculus, we usually neglect the third order. We say third order is very small. The resulting second order are substituted in the right-hand side to yield. Like I said, I repeat, you can re-derive all this equation on your own. I'm not deriving them, I'm just saying this is the way it's done. Equation 7 describes convection and diffusion, and it is a parabolic type. It now only has a second order derivative with respect to space. This is partial h with respect to x squared, the way Hayami would have liked it. Hayami or Du. But it has a very complex term in here, which now has the a's and the b's. These are our a's and b's, 1 or 0. Look at this. Okay. The left side is Seddon's formula right here. The right side is the what I call the dynamic hydraulic diffusivity, as opposed to kinematic hydraulic diffusivity, which would be that of Hayami. Now that's a new term. I actually introduced that. Since we worked on this for 25, 30 years almost, we had to introduce new terms to make it so it's clear and not confusing. Okay, so equation 7 qualifies as a generalized diffusion wave equation, which includes inertial effects in its description of run of diffusion. Accordingly, the diffusivity of equation 7 may be properly referred to as inertial hydraulic diffusivity. So excluding or including the inertia terms, equation 7 specializes into the following models: non-inertial, convective inertial, local inertial, and full inertial. So the non-inertial model of Hayami and Conch is obtained by setting A equal B equals 0. And we get this number over here, very simple. That doesn't have any Fruit number or Vedenikov number dependency. The convective inertial model is obtained by setting A equals 0 and B equal to 1, and we get this number in here. This is interesting because if you notice, we talked about 1 minus Fruit number in some parameter, and this one has a plus. So it is already kind of odd. We'll see how odd it is later on. The local inertia obtained by setting A equal the opposite. In the prior one, it was A0 and B1. Now it's A1 and B0. And now we get a minus in there. Minus is a little better than plus. Why? Because it means that this number will go to 0. This over here will not go to 0 ever, no matter what for a number. So this one is not really natural. Okay? It's not really natural or physical. We'll see it. And the full inertial model is this one, which reduces to the Doog equation. Remember, the Doog has a 1/4 before the Fruit number. 1/4 is 0.25, so it matches the Doog equation. So the generalized formula, our generalized formula is with an alpha, where alpha varies between 0, 0.5, minus 0.75, and minus 0.25. Okay, hydraulic diffusivity is dependent on the Fruit number. Okay. The hydraulic diffusivity of the non-inertial model is independent of the Fruit number. That's a Hayami formula, which limits a non-inertial model to low Fruit number flows. And now this is interesting. I think we said in the previous paper that it does, the effect of the Fruit and Vedenikov numbers on the diffusivity is small. Well, that depends on how much flow are you running through. If you're running hydraulics with large flows, it may be a substance. But if you're running hydrology with relatively small laminar type, very small depths, it may not be a substance. You'll have to really work hard to get some showing on the difference between the kinematic and hydraulic diffusivities. This is the work, by the way, that Andrea is going to do as part of her term project. She will run a model that will basically determine under what conditions, area, physical, everything, all the parameters. There's about 15 parameters in that model, which with judgment, of course, you just can't arbitrarily vary the parameters. You got to use some judgment, otherwise you'll never get out of the answer, get the answer out of the problem. Okay, you have to do some analysis in there. So we expect some light in the next few weeks on this issue of when, if at all, can we say that the dynamic hydraulic diffusivity is useful. I'm convinced that it is, but you have to work hard. We have to work hard at it to find it. Okay, so the hydraulic diffusivity of the non-inertial model for high fruit number flows, it would tend to over-predict the hydraulic diffusivity, right? Because it doesn't vary with the fruit number or the Vedelnikov number. The hydraulic diffusivity of the convective inertial model is fruit number dependent, but increases with an increase in fruit number. And there's some calculations we have done in here. So we've seen in the convective inertial model and the local inertial, the convective inertial model has a A minus 0.5, and the other one has an A plus 75. So they have an opposite behavior. The second one is actually not quite good. When you combine them, you have 0.75 minus 0.5, we get 0.25, which is closer to the non-inertial model. So basically we're saying that, therefore we conclude that the non-inertial model is a better approximation of the full inertial model than the other two. We got 4. But the simpler one, which neglects both, it's easier and better, a better approximation of the full inertial model than the other two. The other two are partial and they're odd. One should not really neglect one of those terms in keeping the other. Now, have we done it? Yes, we have done it. People do it, but they should not be done. Why they do it? Because they don't know what we're talking about here. They really kind of depart or diverge from the right answer. The best thing to do is either consider the whole thing is in a full inertial model or just drop both inertia, considering that it to be small. So the conclusions of this paper, we come up with a generalized diffusion wave equation on the basis of the linear analogs. Specialization of this equation leads to the following 4 types of diffusion wave models, depending on whether the inertia terms, local and convective, are excluded from or included in the formulation. Full inertial, that's the Duke model, local inertia, convective inertial, and non-inertial. Non-inertial is the Hayami model. Analysis of these diffusion wave models reveals substantial differences in the behavior, particularly with regard to the fruit number dependence of the hydraulic diffusivity. The full inertial and local inertial have neutral fruit numbers, while the convective and non-inertial models do not. Okay, so we're basically saying don't neglect only one inertia. Neglect both if you have to. In other words, you can go Duke or else go Hayami. Notice that I did not mention Vedelnikov in this entire paper. And the reason for it is that this paper is dated 1990. This is the original paper. Generalized diffusion wave equation with inertial effect in water resource research. And our Vedelnikov paper that we have already read was published in 1991. It was published in 1991. I should tell you a story about this because you know Professor Ponce is Professor Ponce, and he's got his stories. I had a disagreement with the editor of the ASCE journal, and he basically told me that, tough, Ponce, you're not going to publish. So for 3 years, I couldn't publish in hydraulics division. So I moved to water resource research, and I was publishing in water resource. So these papers that you see in water resource research is basically because I was banned from publishing in my journal, which is the ASCE journal. And the reason for it is simple. Sometimes you have editors that move in, and there's disagreements. You know, there's disagreements everywhere. People disagree, and he disagreed with me and strongly, and that was it. But when he moved out, because nobody is forever at a position, When he moved out, I was able to go back to the journal. So in 1991, right after he moved out, I submitted a paper and I published several papers later on, 1991, 93, 95, in, ASE Hydraulics. But Water Resource Research is also a very good journal. I mean, AGU, so this is a very good journal too, Water Resources Research. So let me cut this over in here. So that's the end of this paper over here. So now I'm going to move on to the second paper, which is dam breach floodway propagation using dimensionless parameters. Can you see it? Green?
Yeah, we can see it.
Oh, okay. I just always checking, because I don't want to be talking without you guys not seeing what I'm talking about. Okay, and sometimes things do not work perfectly. Okay, so we're kind of shifting gears in here. We're still talking diffusion, but now we're going to move into the area of dam breach. Dam breach floodway propagation using dimensionless parameters. Now you guys know that from my work on the S-curve back in 1977, it's been 44 years. I kind of got enamored with the dimensionless parameters. So I figured that if you have the right way of non-dimensionalizing a problem, a hydraulic problem, you could end up with beautiful things because you could solve a problem once, like we did in the S-curve. We solved the problem once. All the others match or have to work with that problem. Okay, and through my experience in hydraulics, that has happened, and it's beautiful. Hydraulics is beautiful because of the fact that you can correctly non-dimensionalize the problem and solve it once. Okay, so the dam breach problem is a serious problem. In the United States, when we wrote our paper on dam breaches, which we will talk about later in the applications part of this class, back in the year 1981, we wrote that paper. We checked on the number of dams in the United States. There were about 50,000 at the time, and 150,000 because the United States held about a third of all the dams in the world. Now it should be maybe 70, 75,000. You're talking 200,000 dams. Okay, many of them are earthen dams, not concrete dams. Typically, a concrete dam will be hard to fail, but earthen dams can fail. Now, then the question is, why are we building earthen dams? We should build all concrete dams. And the answer is no, you can't, because some foundations can't hold the concrete. I recently visited the dam in Vegas, in Las Vegas. I was in Las Vegas visiting, and we went over to, I always forget the name of this dam. Can't forget. Well, it's very close to Vegas, within an hour. And it's a huge dam, and it was built in 1931 to 35. So it's going to be more than 90 years. That dam's going to be there forever. If we can dimensionalize or figure out what forever is, it's forever because of the massive structure. Is solid concrete. It's not going anywhere. Okay. Now, recently, in the year 1983, the spillway was tested for the first time. That spillway was built in 1935. I have a video on it, by the way, and I will put it on the stuff for you to see. Because when I was there, I did a video, nice actual video. So I learned what I already knew. It was in the back of my mind that the spillway of the Las Vegas dam, not Vegas, the dam was not used since it was built. It was only used in 1983 with the El Nino event. The strongest El Nino event of the century came in 1983. It affected the entire Pacific, and it affected also the area in the United States. They had a huge flood, and they tested the spillway, and the spillway worked really well. That was the spillway of this dam, but downstream, the Glen Canyon almost failed. Why? I can't tell you. I don't know the information. My guess is that the Glen Canyon Dam, I'm going to guess here. Maybe I should not say anything. Maybe I should keep it at this. The first spillway on the Colorado did not fail. The second one did fail. So subsequently it was fixed. We learned a lot from the failure and so forth, but that's another story. Okay, So out of the 50,000 dams, many have failed. We have a paper that we recently posted on the web. I'm also going to put it in there for you to read, which shows that paper was written 40 years ago, and it shows what happened in many, many failures of dams in the US, mostly earthen dams, how it happened. And there is a field called dam failure, and there's a lot of people that work in this area. So we felt at the time that we were confident that we could do this work. Luckily, I had Professor Ahmad Taher Chamsi from Iran, who visited at that time. There was a year 2003, San Diego State, with a sabbatical. And he came over to me and wanted to sign up in the lab. And he said, Professor Ponce, I'd like to work with you. And he had a year. They gave him a year. Note that in the US, they give us 6 months. In Iran, they give them a year. So Mexico is also a year, by the way. We should really complain that we're not getting a year of sabbatical here in San Diego State. Whatever it is that he came over, and I said, I picked him up and I said, yeah, you can work here. He seemed like a nice guy. And then he said, Professor Ponce, I got to tell you this as we start. He said, I've got to write 3 papers. 3 papers. I said, no problem. Don't worry about it, because I am a writer. I can furnish you with 3 papers in the year you're going to be here. A paper every 4 months. I was joking, but that's true. And he did do 3 papers. So then I gave him this subject, because I said it was a good subject, a subject that was guaranteed publication. Because sometimes you don't know if the publish is good or bad, or, I mean, the reviewers can get mean at your paper. I mean, that's a fact. It has happened. So I said, this subject is foolproof. We're going to publish it. But it's a lot of math. Can you do the math? He says, I got a degree over at Oxford somewhere out there in England. Okay, good. So he did it. He did a great job. Ahmad Taher Chamsi, he's still out there in Iran teaching, I'm sure. And this is the product of the work of Taher Chamsi. But it is based on a hunch and a confirmation. I had a hunch that this would happen because I know the subject. And also, I confirmed it with Danny Fred. Of the very few times, 3 or 4 times that I ever spoke to Danny Fred, physically, like in presence, I said, Danny, what do you think about this? About the fact that if you route a dam breach floodway, that no matter what the peak of the flow, the downstream is going to match. They're going to match somewhere. Somewhere downstream, which you got to calculate, you're not going to have a difference in the stages, discharge and stages. And he said, you know, Ponce, we run hundreds of these tests with a dam break. He was at the time the developer, not at the time, he had developed dam break, first DWAPR and then dam break specifically back in the middle 80s to calculate the dam breach problem. That was Danny Fred, F-R-E-A-D, the great Danny Fred. But however, though, later on, 2 things happened with dam break. First of all, Danny passed away. Everybody's going to do that eventually, right? He was young when he passed away, maybe 65 or 70. So his model had no person, I guess, to defend it over the National Weather Service. And at the same time, the people at HEC got really strong because they went gooey, you know, and they started kind of taking over from other agencies. So now HEC is the only game in town. You run either RAS, which has 5 or 6 arms of HEC RAS, I mean sections, or you run HMS and hydrology, hydraulics. There is, to my knowledge, I could be wrong, I'm not 100% right, there is no other federal agency that is supporting broadly used programs, software programs, to be used by everybody, not just the in-house people. SCS doesn't have it, they used to. Army Corps Portland doesn't do it. You know, a whole lot of other people. Bureau of Reclamation doesn't do it either. Nobody does it. The only people that do it are the Davis Lab, the HEC Davis Lab up here at Davis, California. That's good. That's good. What can I say? Okay, so we did this work, and I said, what we need to do is we're going to run through my S-curve methodology, and we're going to non-dimensionalize it in the way that we feel better, you know, and we have some experience with that. And we did come up with this dimensionless peak discharge. See, you can see this. This says, this is the dimensionless peak discharge. Peak over relative. So it's over a certain dimensionalizing parameter. Okay. And in here's a dimensionless distance. The x, actual x, physical x, over L sub O, which is R L sub O. You know, L sub O is the trick to dimensionalize in space anything. Okay, so you can see there's three failures, three different types of dams. One started high, another started middle, as low, and they all ended up in the same place, like almost exponential, almost Horton type of, this is a Horton type of formula, isn't it? In other words, it starts off flat in here, but eventually gets to be some exponential Horton type, or exponential. I don't want to give it to Horton, just exponential. So we say in here, we got to go a little faster here, otherwise we're not going to finish. Analytical model of floodway propagation. I'm not going to get into the math here. I'm just going to show you the results. An analytical model of floodway propagation is used to study the sensitivity of dam breach flood waves to breach outflow hydrograph volume, peak discharge, and downstream channel bed slope using dimensionless parameters. Dam breach fruit number is defined to enable analysis of a wide range of site and flood conditions. It is found that at a certain distance downstream, the attenuated peak discharge is independent of the magnitude of the discharge at the breach. How fascinating. And that's exactly the hunch I had, the hunch that had been confirmed by none other than Danny Fred when I visited over East Coast sometime back in the 80s. It was 80s and 90s even. So flash floods, we already know flash floods, we know the problems, we know the Teton Dam failure, which is a terrible disaster. Okay, I can expound later on as to why did that happen. Breach outflow hydrograph is a function of the geometric and hydraulic properties. Right, so in an earthen dam, how is the breach going to happen? First of all, like in the case of Teton, of which, by the way, I have a video of Teton, I'm going to post it too. Let me write it down, otherwise I have so many things in my mind that I'll forget. I have the Teton and that other one I'll remember later on. Okay, so the breach outflow is a function of the geometric and hydraulic properties of the reservoir. Like in the case of Teton, it will depend on the material. You're eroding material. The size, the interaction between the water and the flow to form the breach. So there's going to be a certain amount of time for the breach to form. If the material is strong, it may take 3 hours, 3 to 4 hours. If the material is weak, erodible, it may take 1 hour, but it does take some time. Typically not less than 1 hour for the whole thing to breach and it come out, the peak flow to come out right after the breach. Okay, so it takes from 1 to 3, 4 hours. By the way, I have another paper on that, which I think we're going to read later on. We'll see. That other paper is a historical paper. It's not a computational paper. So perhaps I have not included it in the reading material for this class. As a matter of fact, that's a paper we did with Chamsey too. That's a number 2 paper out of 3 papers that he had to write. Okay, so for any given reservoir, the dam breach flood peak is inversely related to the flood duration. That is correct. The longer the flood, the lesser the peak. Why? Because the volume behind the dam is a constant. And the volume's got to spread out. So you know that if you spread it out, you're going to have a lesser peak. That's the essence of the meaning of the unit hydrograph, right? So we know that. It follows that several postulated dam breach outflow hydrographs may eventually attenuate to about the same peak. In other words, what's this for? What are we doing this? Well, basically, we do not know the outflow breach because the value of the discharge that breaches, we do not know. Because in order to do that, we would have to know the dynamic erosion or erosive conditions on the dam. And that's not known. Why is it not known? Because it's in the verge between hydraulics and soils. And and we just don't know how to do that. So why soils? Because that's the dam. The dam has been built by soil mechanics. Hydraulic engineers don't build embankments. That's built by the soil mechanics people. Okay, I remember when one of my first jobs back in the early '70s, I was one of the first people to go out there to Poechos Dam in Peru, in northern Peru. I spent 3 to 6 months out there, but I was involved with the soils. Remember, I told you at the beginning of my career, I was geotech. I started geotech. I was involved with soils. There were two groups of people out there: the hydraulics people and the soils people. And I was involved with the soils people. I didn't get to know the hydraulics at the time. I wasn't really interested. There were two jobs out there to be done: soils, geotech, the embankment itself, and then the hydraulics, the overflow spillway, and so forth. So there's divisions in there. So again, I reiterate that the issue of how, at what speed does an embankment, a compacted embankment, fails, that has not been solved yet. So then we have to estimate. But the good thing about it is that whether you estimate 1 hour or 2 hours or 3 hours, you get 3 different peaks. But those 3 different peaks are going to meet downstream. So if you were to do this calculation and figure out where they're going to meet, because you can with our methodology, or you can run a dam break for Precras, as we have one of you guys doing it. I think Cassidy is doing that, right, Cassidy?
Yeah.
Yeah, Cascade is going to run Precras with dam breach, right? With the dam breach feature of Precras. So she's going to tell us how she's going to do it. So if you with Precras, you can try 1, 2, and 3, low, medium, and high. And if we're correct, and I know we're correct, you will route this downstream and end up at a place where the stage is the same for all 3 cases. So then you can say, I had a, well, I'm not prepared to do that right now. Well, let me just do it. What the heck? We're spending a lot of time on this, but okay. So we're going to have something like this. Can I do this? Okay, I think I can. I'm unable to expand this. I won't be able to do it. Okay, well, let's say that I'm not good at this still. Let's say that that we find the location where these 3 hydrographs should meet. So then we can say that if a town is downstream that point, you already know the flood on that town. But if the town is upstream, depending on how close it is to the dam, you really don't know the size of the flood. You might as well go conservative, meaning the high flood, not the low flood. You understand what I'm saying? If you're close to the dam, it would matter which of the 3 solutions. But if you're far from the dam, it doesn't matter because they're the same as far as the attenuation, that is the diffusion, is concerned. So that's the good thing about this methodology, that it will allow you to separate the places that are going to be in danger of being flooded with an unknown value as opposed to another one that is flooded with a known value. Or all 3 of them will coalesce at a certain point downstream. So we have the theoretical background over here, same thing. And in here I'm going to bore you because I'm going to write the same equations for a 3rd time that I've already written all over since the S-curve. They're all in here. You will relate to these equations. They're all the same. Then we develop the model. In here, we're talking about developing an exponential decay, right? Because it is an exponential decay. So equation 22 is the exponential decay. And then we figured out this formula based on our S-curve analysis. And then we get the attenuation and so on and so forth. We make some assumptions in here as far as the volume. And we finally get the, let me see the alpha in here. Right. And number 24 has an alpha in there, alpha star. So that's the critical number here. And alpha star is 34. So it depends on the slope. It depends on all these other values. I'm not going to get in there because it's very intricate. Okay. So we finally get an application. We have an application in here. and we have the answers. For various references, we had to dimensionalize, non-dimensionalize everything in here. For various conditions, unfortunately, ASCE was very, how can I say, I don't know what they were doing, saving paper or what. They had recently changed to a different format, from a small format to a large format, and they put all my graphs in very small print. So then when you blow them up, you can't read it. That is unfortunate, but that is a fact. So we got these three graphs for the first case. The first case is 27,000 cubic meters. That's per unit of width, by the way. We did this per unit of width. That's the only way we could fully dimensionalize it, non-dimensionalize it. 24, 27, 54, and 108. Over here it's 108. And then we get this table which shows the answers. It says that for example, and it's in the book, for 54 and for a slope of 0.001, which is a mild slope, we get the Q of 3.18 at 5 kilometers for a mild slope. But if it's not a mild slope, if the slope is 0.001, it's 134 kilometers. And if it's 0.01, it's at 10,000 kilometers. 10,000 kilometers, it surrounds the world. Okay, so see the sensitivity of this stuff, which means what we already knew. If the downstream slope is mild, it will attenuate. If it's steep, it will not attenuate. And the range is practical. 0.01, yes, certainly. 0.01 is a standard slope in mountainous regions. And 0.0001 is flat, like in Florida. Florida is even less than this. So you got attenuation. So as you can see, these numbers quite match what we have said all along, the theory of the diffusion wave. So we conclude in here, and I've already said that, so we don't need to repeat. So what I want you to do is to read this paper critically to understand what we've said. You probably will not be able to understand the actual numbers unless you spend a lot of time, which of course you're probably not going to have. But I do want you to know or to realize what we have done in here. I summarize, I say, we took the equations, put them together with our formula, our S-curve data, which handles the diffusion of the waves, of the flood waves. We put it at per unit width, which was necessary for putting everything into one graph. Otherwise, you couldn't do it. Per unit width, normalizing the discharge. We normalized the discharge to per unit width. And we were able to come up with this presentation, which is a good presentation, and it explains what's actually happening out there in the field. Okay, so with that, I'm now going to go to the third paper, and we got 25 minutes. I think we can do justice to this third paper. This third paper is very important. The first paper wasn't very practical. The second was practical to an extent that we're interested in the dam breaches and how they behave. This paper is really practical. This is the third paper. This is the foundation of most of the work that is done in hydrology, okay, particularly for hydrology. That's why this class is called Computational Hydraulics and Hydrology. So I'm going to be talking, the subject is linear reservoirs and numerical diffusion. Does everybody see the green sheet?
Yeah, we can.
Okay.
Yes.
Okay. The story of this paper. For the nth time, Professor Ponce and Mr. Lucky. I went to Brazil in 1979 on a consulting assignment. They hired me for 2 months to take the SAR model and implement an upstream model that would feed the SAR, the discharges, with dams and without dams, so that they could analyze the downstream flow with the SAR model. So I was supposed to develop the input for the SAR model and run the SAR model. So at that point, when I got hired, they told me they already had installed the SAR model in Rio de Janeiro, and I was going to run it. So I already had a PhD. That was in 1979. I got my PhD in 1976. But I never heard of the SAR model. Why? Because there's so much stuff out there that you can't, even at Colorado State, you can't learn it all. I mean, it's impossible. I already told you there's 100 types of hydrology out there. Hydraulics, at least 50. Hydraulics is more diverse, by the way, because it covers more ground. Okay, so I immediately picked up the manual, the SAR manual, ordered it from the Army Corps Portland, and got the SAR manual and started reading it even before I went over there, because I knew I was going to be confronted with it. And I would have to be smartly talking about the SAR model as if I knew, okay? So within a couple of days, I knew the SAR model, okay? So then I went over there and we did the runs and so forth, spent 2 months of my life out there, and we did a good job and had a lot of fun, and we learned a lot. And when I came back, I realized that I knew a lot about numerical diffusion, but I did not know a lot about linear reservoirs. Linear reservoirs was not in my experience to that day. So I learned the linear reservoirs in Brazil, particularly the SAR model, which is it's called the Cascade of linear reservoirs, of which it was the first time I ever heard of it, by the way. The Cascade of linear reservoirs sounds like a thing that you would pull out of somewhere really fancy. Cascade of linear reservoirs. But then if you go to Chow, the 1964 book of Chow, the Handbook of Applied Hydrology, and you look up, it's a very thick book. It's about 3 inches thick. It's about 1,500 pages. The Handbook of Applied Hydrology. By the way, that handbook has been superseded. Maidman, who is the last student of Chow, and who wrote the Chow, Maidman, and somebody else book in 1989, David Maidman. In 1993, came up with the second version of the hydrology book, or Handbook of Hydrology, and he did not, for whatever reason, I didn't ask him why, he did not include Chow there. After all, Chow had been dead for 10 years, right? So the second issue of the Handbook of Hydrology is called Handbook of Hydrology by Maidman, Professor Maidman from University of Texas, I believe, Austin. Okay, so it is, what I was saying is that it is in Chow 1964. I haven't checked the Maidman book. So then I decided to write this paper because I felt that there was a link missing between numerical diffusion and the linear reservoirs, because a reservoir produces diffusion. And in our models, we could have a kinematic wave which is not supposed to diffuse, but if we set it up in the numerics to do diffusion, it would behave like a reservoir, exactly a reservoir. So there were some really good analogies between those two concepts, linear reservoir and diffusion. Linear reservoir is a theoretical concept which produces diffusion without the benefit of numerical diffusion. While numerical diffusion is a numerical concept in the grid approach, which always produces diffusion. Actually, not always. If the Courant number is 1, there's no diffusion. You know that already. So I figured I could write a paper. I was in the business of writing papers at the time. I had to write papers, write, publish or perish. So I wrote this paper, which was a good paper. It was well accepted, readily accepted, and it was written in a clear way, and therefore much read. Okay, so let's take a look at this paper. Conceptual models of hydrograph synthesis are presently being used to simulate watershed response. So we all of a sudden are in hydrology now. Cascade linear reservoirs is a useful tool in applied hydrology. It had been used by the people that developed the SAR model back in the 40s and 50s. I believe it was Don Newton. I could be wrong on the name. Yeah, I think it's Don Newton. Don Newton could be considered the father of American modeling, hydrologic modeling, because he was the first one that came up with a model back in the middle 50s. I had the fortune to actually meet Don in person when he was a very old gentleman already back in the 80s, I believe. I met Don Newton, none other than Don Newton, the creator of the SAR model. Okay, so that's the SAR model. Interestingly, though, the Japanese had already built parallel, I'm not sure exactly the dates, but parallel to the work that Don Newton did with the Army Corps in Portland, in the Portland district, the Japanese had already done the tank model, and they published it extensively, and the tank model is also based on the Cascade linear reservoirs. And I do believe that there's other places around that have also used it. I don't know if it's following Don's. It's a simple thing. It's a very simple tool that could be used by anybody, by the way. When I wrote my book back in 89, 86 to 89, I decided to make a big deal about this cascade because I knew it. By that time, I already knew it back and forth. So if you go to my book, I actually make a big deal about the cascade of linear reservoirs when most other hydrology books don't even mention it, okay? Because they feel this is a rather specialized thing that only if you use the SAR model, you'll be running with it, against it, or will be confronted with it, or the tank model, but that's a Japanese model, right? So most people think that the cascade is a little bit odd. I didn't, because I had used it and I had run into it when I was in Brazil in my consulting. So I put it in the forefront of my book. In chapter 10 of my book, there's 3 methods, and one of them is the cascade. There's umpteen methods to do Watershed modeling, but I only chose 3 because I had to showcase, right? So we have in here. So what's a linear reservoir? That's equation 1. V equal KO. V equal volume or storage, K is a coefficient, and O the outflow. Interestingly, Mr. Nash, who is a professor out there somewhere, I believe in Ireland, also in Ireland, not quite sure, 95% sure, Nash is in Ireland, I think. I could not really follow Nash's work for reasons that he's a very highly mathematical gentleman. And I'm a mathematician too, in some sense. Engineer has done a lot of math, but math is like that. It can get intricate and then you don't know it. You simply don't know it, okay? So I present in there the function that Nash has in his book, which was repeated by Duke, by the way, I believe. And this is equation that has in there the gamma function and so forth. The numerical analog, and I'm more like numerical rather than analytical because I grew up with the computer, right? Some of these gentlemen, including Nash and Duke, grew up before the computer time, so they really became analytical. People do what they have to do at the time they lived, right? So in here, the synthesis and reservoir regulation developed by the Portland district. The time of storage is equivalent to the storage coefficient. These people use the same concept in different names, so we don't get to be confused in here. We should not get confused. The tank model developed by the National Research Center in Tokyo, Japan, among the streamflow simulation models that base their routing component on the cascade. The cascade, now, here, don't forget that I'm talking about the cascade with my knowledge of the 1980, I believe, which is much less than what we have now. In the year 2009, I struck luck. I'll tell you later when we get there. That will be Wednesday when we get there. And we should not tell the story now because it will be extemporaneous. But in the year 2009, we improved all the stuff completely. And this is the year 1980, so that's almost 30 years later. Okay, so we have in here the, we are saying in here that you can, what I said earlier, that if you take the discrete function and put it as if it were a reservoir on the right, you take only the right, like the convex method. No, not the convex method. Like the Muskingum, with x is equal to 0, you'll be running a reservoir no matter what. When x is equal to 0, you'll be running a reservoir. So then we say that kinematic wave routing can produce numerical diffusion. You already know that. Everybody knows that. And these are the same equations that we have been talking about all the time. And then we have equations 8, which is you already familiar with. I had homework number 2. I had you worked at this equation to confront the equations of Conch with that of the gentleman from England, Price. Price had written that report. This is Price's equation, number 8, which we use all the time. We used in our book. I had you prove it, by the way. And then the Scurra number, which we all know, and the Sell-Reynolds number. Now, Professor Ponce is the only one that does a big deal about the C and D, by the way. If you go out there and look for it, you won't find it. I don't know why. I think this simplifies things, but some people don't agree. That's, their privilege not to agree with something that is simple. They want to perhaps make it complicated. Some people are actually looking for complicated stuff. At any rate, we have all these equations which you already know. We've repeated them many times. These are all the same equations. The classical approach to the Muskingum method. That's the classical approach. Everybody, well, not everybody, but we know from Chow, from his book on Chow, the classical approach of Muskingum's been around since 1938. So it's almost 80 years old. There's still people that work on the Muskingum, by the way, that kind of hold on to, what's the word in English, to hold on to something that is old but is good, good for them anyway. And they continue to do it. They continue to use the Muskingum. At this point, to be honest with you, I do not believe there should be anybody in the world that is actually working with the Muskingum. They should be working with the Muskingum conch, but I can't convince anybody. I'm sorry, I can't convince everybody. Some people are going to continue to do what they have to do until they die. Okay, examples abound. I'm not going to spend time on it. Okay, linear reservoirs. The concept of linear reservoirs, the linear reservoirs of Nash, the linear reservoirs of Doog. Okay, so linear reservoirs is a widely known concept in hydrology. As a matter of fact, the KM, the Kalin-Emmel-Yukov method, is one way of looking at the linear reservoir. And I briefly talked about this method before. I myself have not done any work on the KM method, the Kalin-Emmel-Yukov. So I'm going to leave it at that. I know that the method is based on the concept of the linear reservoir, which we're talking about here. And then the SAR routing equation. The SAR routing equation is a particular case of the Muskingum method in which the concept of reservoir type storage is implemented by setting x equals 0. In other words, if you take the Muskingum and set x equals 0, always x equals 0, which is the same Kalin-Emmel-Yukov method, then you end up with the SAR routing equation. It's amazing. All these methods are more or less the same. They all work with the concept of diffusion, either numerical or physical. So what we have in here is that when x is equal to 0, it immediately implies that RD is equal to 1. So when we substitute RD over there, equal to 1, that is like D does not exist, and therefore we get C1, C2, and C3. In this particular case, C1 is equal to C2, equal to C over 2 plus C. There's no D there. The D has been confounded with the 2. The 2 is 2 because it's 1 plus D with D is equal to 1. And the C3 is a little bit different, okay? And we substitute these equations into equation 4, gives this formula, which is the formula in our book. This is a formula in our book. That's the formula that it should be, okay? However, there's always a however here. Don Newton and his crew over there or his group out there at Army Corps Portland disagreed, or they could not find equation 20, but they found equation 21. And they're the same. And I believe I ask you to work yourself up with the algebra and prove that in fact 20 is the same as 21. Because if you don't work at this, then you will not agree with it. They give the same answer, though they're the same. They're equivalent. But equation 20 is the correct equation that's in my book. Equation 21 is the equation that is in the SAR model, and they're the same, okay? So I'm going to have you do that fun exercise, but later on, prove that equation 20 is the same as equation 21. And finally, we get to the cascade of linear reservoirs. So we know what is a linear reservoir. So we're going to set them up as a cascade, meaning several linear reservoirs. Why? What's the advantage? The advantage is that if you use 3 linear reservoirs in series, you are going to, every time you use it, it's in series, right? One after the other. Every time you use it, you're going to be producing more diffusion because the element of a reservoir produces diffusion. So it's like you add another parameter, which is the number of reservoirs in the cascade, and therefore you can get any diffusion that you wish to get out of the problem. You can calibrate the answers to the diffusion. And that's the way it was done by Don Newton. Okay, equation 21 is used in the numerical model of a cascade of linear reservoirs such as the SAR model. Okay, close example. This is interesting. It merits a little bit of this discussion in here. When we did the work in the Pantanal back in the year 1979 and 1980, we were using the SAR model that was already established. I did not choose the SAR model, but in retrospect, at that time, that's the only thing they could do. The only model in the US that had been developed to the point that they could be used by other people was the SAR model. This was 1970s, 1980. So all they had. There was no other of the newer methods that came up later on. HEC did not exist at the time when the Brazilians chose the SAR model. They cannot be blamed for not choosing HEC, okay? Because they did not do. At any rate, the SAR model worked reasonably well. It was calibrated. They had a lot of data, but it was not perfect. And the reason why it wasn't perfect was because of the peculiar way of functioning of the Pantanal. It overflowed, and when it overflowed, then you were left to figure out what the routing parameters should be. And it was a tough job. They did what best they could, but they kept getting an answer which was not correct, not 100% correct. So what they did, the Brazilians, in their smartness or whatever they did was, since they were using this model for forecasting, they forecasted a week. So they could say, based on what we know so far, in the next week, we have all this precipitation, big basin, 140,000 square miles, and this is the answer. But if they didn't get the answer in a week, then they would correct it. They would go in there and correct their model, parameterize the model again so that they can get another answer for the next week. So they were following basically the flood and be humble enough to say, we're going to do this every week. We cannot do it a month in advance because we're going to mess up. That's cool. That was nice. I am sure that the National Weather Service must do the same thing because modeling large basins, it's tough. Simple basins, small basins, easy. Large basin, why is it tough? Because you never know, you don't have a 100% certainty on when and how is it going to rain. And you're trying to convert the rain to flow. If you make a mistake or the rain doesn't come here and so forth, it could be a problem. So at any rate, equation 21 is used in the model. Now, interestingly though, for the Courant number, when the Courant number is equal to 2, we get these answers on the left. 1 reservoir, 2 reservoir, 3 reservoir, 9 reservoir. We did all the way up to 9 reservoirs. As you can see, the addition of every reservoir creates more diffusion. Correct, that's the way it should be. But the diffusion is not that high because the Courant is 2. Any Courant greater than 2 would blow things up because it would mean like you told them that it's not a diffusion. This system is not diffusing. Other than diffusing, it's amplifying. So therefore, the mathematics is in there. It's so beautiful in there that it blows up completely. You try this model with C equal 3, and you get garbage out of the computation, okay? In order for it to run, you have to run it with 2, in which we get this. And interestingly enough, the C equal 2, 1 reservoir is a rational method. The hydrograph of the rational method shows up here. The isosceles triangle, which is the rational method hydrograph, which means the rational method theoretically has no diffusion. Right, exactly. There's no diffusion. What you have in the CIA, the C is abstraction, it's not diffusion. If you consider C equal to 1, the answer is IA, which has 0 diffusion, which is over here. This 50 over here that you see in there is the IA. Okay, so this is the rational method hydrograph. Then all the others are modified according to the number of reservoirs. Then C2, C.08, you got more diffusion. C.04, you get more diffusion, 0.02, 0.1, 0.2, and 0.1. So this is the typical range for running this thing. For C between 2, which has hardly any, if nothing. For C.1 has a lot of diffusion. And for 0.8, there's a lot of flexibility in here to pick and choose any translation and any diffusion that you wish. And that's what makes this method a good method in the sense that it's a bag of tools and it gives you the answer as long as you know the C and the N. And for that, you can count on measurements or you can count on experience. Some people have seen it so many times that they already know what the answer is. You can say 0.4 and 5 reservoirs and run with it because I know I've already done this calculation many times and that's what works. That's experience. If you don't have experience, you cannot do that, okay? Because things have a way of repeating themselves. Okay, so you already saw the answers for this thing, and it works nice. So the answer is, for a given Courant number, greater number of linear reservoirs results in smaller peak flows and longer delay times. For a given number of reservoirs, smaller Courant numbers result in smaller peak flows and longer delay times. The skewness is also a function of the Courant number. Courant number increases, the positive skewness, right, fast rise, slow fall, decreases, as you can see in there. Courant number tends to value equal to, the skewness vanishes. For the rational method, for n equal 1, there's no skewness whatsoever. Not even, no skewness, there's no diffusion, no skewness. The integration of the area under the computer hydrograph shows that the method is mass conservative. 100% mass conservative. It is, it always never ceases to amaze me how this thing works. You run millions of numbers, and then you integrate the hydrograph below the area below the hydrograph, and it gives you the right answer. No mass loss. But that's these simple methods, because the complex methods of the dynamic wave type, they have mass losses. Even the Muskingum-Ganj nonlinear has a certain amount of mass loss. Okay, I believe Andrea is going to do the work, right, Andrea? Right. Andrea is going to work on her term project, the mass losses of the nonlinear method. Oh no, I'm sorry, I take that back, Andrea. I think you reconsider that, right?
Yeah, I think we ended up changing it.
Yeah, right. Yeah, basically, I thought about it, and I said she is going to redo work and confirm what you had done. That's nice, but there's a better project out there, which is one that we have not done. I think so. Andrea decided to change. So I'm sorry I said that. I'm not perfect. I sometimes forget things. Okay, so this is summary and conclusion. I'm going to leave this for you to read on your own. We've got a couple minutes here. I do want to get into here, the calculator. Okay, we have calculators for a whole lot of things. And next time on Wednesday, I'll show you some of the things, really fancy stuff. But in here, I'm going to run the example. The example says the time interval is 1. The storage is 2, the storage constant, K. This delta T over K has to be less than 2. So I cannot run a time interval of 2 and K2 because it will be a problem. So 1, 2, 16, and this series in here, this series of inflow hydrograph. Copy, return, 1, delta T, 2 for K, 16. And then I'm going to have in here, I'm going to paste my record in here. Cool. Okay, I got the record paste. Okay, so now I'm going to run this, the linear reservoir. I ran the linear reservoir in here. That's a linear reservoir. The inflow was 100 to 1,000 because it's over here. The inflow started at 100, went 150, 250, 400, got to 1,000, 900, 700, and went back to 100. 100 is supposed to be the base flow. Okay, so this is the inflow over here. You can see the inflow over there, 100 to 1,000 and back to 100, right? Every hour, every hour, right? Delta T is 1 hour. These are the calculations of the linear reservoir, as you see. Normally start at 100 and end here at 142, 100.452, only because we didn't trail it, we didn't follow it through. If we follow it through more 25, 26, 27, 30, 35, we would get back to a zero, I'm sorry, to 100. I guarantee, because we've done this hundreds of times. And note that the peak is 7:57, and it occurs 3 hours later. The peak is 7:57, 2 hours later. Right here, 2:07. So this is just a sample of a calculation with a linear reservoir. Later, on Wednesday, I'm going to show you samples of calculations with much more complex stuff. That is the Cascade itself. The Cascade, we have calculators and programs for the Cascade. We had a student, let me finish by saying that we're going to read a thesis of a student that was done 3 years ago, where he did not develop any calculators. He used several calculators that we have in the lab, and he developed a thesis around the calculators, like tools that you could use, like software. and his thesis was, we'll get there. We'll get there on Wednesday. This is the Ariza paper. Let's look at it right now. Right here, application of the general dimensionless unit hydrograph using California watershed data. It's a thesis. We're gonna take a look at the thesis at the end of next class. This is on Wednesday. So with that, I exceeded my time, so I'm going to stop in here, and I'll see you Wednesday.